In this video, we're going to learn about permutations and combinations. So there's a really big difference between these two, and that's the main focus of this. But before we start that, we do need to define a new term, and that term is going to be a factorial. Okay, so a factorial looks like this, and factorial, and it kind of looks, it's like an exclamation mark. Okay, actually, it is an exclamation mark. And what it does is it's a symbol to show that we're going to be multiplying that number all the way back down to 1. So for instance, and you can kind of see here, we have n factorial would be n, the number, and then n minus 1, so one number less than that number, and then n minus 2, all the way till we get to the bottom. So as an example here on the side, I'm going to do a real quick one. 3 factorial would be 3 times 1 less, so 2 times 1 less times 1. And that's it. So whatever this is equal to, 3 times 2 times 1, in this case 6, that means 3 factorial is equal to 6. Okay. Also, as a note, if we do have 0 factorial, that means that that's going to be equal to 1. Okay, so this one right here, 0 factorial, because there's no actual definition for that, we just say it's equal to 1. Okay, so let's go ahead and try an example just so we can make sure we know what we're doing here. Let's say I gave us 10 factorial. Okay, well, this would be equal to 10 times 10 minus 1 is 9, 10 minus 2 is 8, and that's where you get that this part right here, where you're just subtracting to get down to the bottom number. So times 7, times 6, times 5, times 4, times 3, times 2, times 1. And then whatever that gives us, I'm not going to actually calculate it. That would be our answer. Okay. Now let's go ahead and look at some examples where we have actual operations. Okay, so here we have evaluate A, 7 factorial plus 4 factorial, and B, 8 factorial divided by 4 factorial. So this one is actually going to be the one I want to focus more on because you're going to see a lot of similar items to this when it comes to permutations. Okay, but let's look at A first so you can see how it works. So for A, we have 7 factorial plus 4 factorial. So 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, and that's all of this part, plus 4 factorial. So 4 times 3 times 2 times 1. Obviously, I don't expect you to do this in your head, so I would go ahead and just grab a calculator real quick. I'm going to do the first one. So 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 5,040. Okay, plus 4 times 3 times 2 times 1. That one I can probably do. See, 4 times 3 is 12, times 2 is 24, times 1 is still 24. And then we add these up. So that's going to give me 5,064. And that's it. Okay, so that's letter A. Nice and easy. Letter B is a little bit more, well, a little bit more work, but it actually works out kind of nicely. So 8 factorial divided by 4 factorial. So when you have a division, notice that, and I'm going to kind of put this here, and I'm going to redo it here. This would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And this one would be 4 times 3 times 2 times 1. But if you notice, you see how they both have that 4? Those are going to give me just a 1 because 4 divided by 4 is 1. Same with the 3, same with the 2, same with the 1. So really, all you're going to multiply is this. Okay? Another way to think about this, that way you don't have to write all this out, would be to go down to that 4. So 8 times 7 times 6 times 5. And then instead of writing 4, 3, 2, 1, we just put our 4 factorial, because 4 factorial is in fact all of this, okay, over, well, 4 factorial. And right away you can see that these are going to give me that 1, and you're left with the same thing, 8 times 7 times 6 times 5. Okay, and then that's all we have to calculate. So let me do that real quick. Okay, and I'm getting 1680 for that. Okay, but either way, if you want to write everything out, by all means. If you want to do it the short way, by all means, whichever one you're more comfortable with. Okay, just for the purpose of this video, I will be doing this method right here. Okay. And I think that's it. Oh, no, we still have, we have more on this side. So now we're going to our actual permutations. So permutations is what we use factorials in a lot of. A permutation is an arrangement of objects in a definite order. So for example, if you think about like let's say you want to do a playlist, okay, of songs, you want them in a certain order. Like let's say you want, the fast songs first and then the slow songs to kind of help you go back to sleep. I don't know, whatever. But that would be an example of a permutation, okay? So here we have that example, a list of songs for a playlist, okay? So there is a formula for this, and it's the following. The number of permutations of n distinct objects, so in this case, the total number of songs, selected k at a time. So selected, let's say 10 at a time, you want 10 songs, but you want them in a certain order. This is the formula you would use that would give us the total number of combinations that we could make out of that, and where order is important. Okay, again, this is super important. Definite order means it's a permutation. So let's go ahead and see this in an example. And we kind of saw something similar to this in the previous section in 12.1. So I went ahead and I'm going to use the horse example again. This time we have 20 horses. So in 2010, the Kentucky Derby had 20 horses into a race. How many different finishes of first, second, third, and fourth place were possible? So it kind of goes back to that counting principle, but now we're going to use it in a permutation format where order makes a difference. So we have a total of 20 horses. So that would be, if we want to write this officially, okay, that would be this part right here. 20 is your n, your total number of distinct objects. And then we want first, second, and third place. So that's 4 spots that we need to choose from. Okay. So when I put this into my formula, I'm going to have the 20 on top. So 20 factorial over 20 minus 4, okay, factorial. And then it kind of looks like what we were doing earlier, but we need to simplify a little bit. So this would be 20 factorial over 20 minus 4. We do subtract that first, is 16, and then we have the factorial, okay? And then from here, I definitely recommend the second method because you don't want to do 20 all the way down to 1, right? That would take forever. So we're going to go down to 16. 20 times 19 times 18 times 17 times 16 factorial. Because at that point, it's just going to, 16 factorial would include all the rest of it, over this 16 factorial. And those two will sort of cancel out because 16 factorial over 16 factorial is just 1. And so we're just left with 20 times 19 times 18 times 17. And this does really go back into that counting principle we saw previously where you have 4 spots, so there's 20 horses to choose from, and then there's 19, and there's 18, there's 17. But this one takes into consideration the order, okay? So we would multiply this out, and that's going to give us, let me see, 20 times 19 times 18 times 17 is 116,280. So 116,280. Okay, that's it for this side, I believe. So that's a permutation. Okay, so we're going to go ahead and look at a couple more things, and then we'll be done. All right, so the one we saw before was distinct objects. Okay, now this one has a formula for objects that are different types. Okay, so the number of distinguishable permutations of n objects, so the total number of objects of r different types, where k1 identical objects are of one type. So you have this many of this type, and k2 is another, and so forth. And this is the formula for that one. the total divided by the factorials of each of those types, okay? Where all of these add up to your total. So let's just see an example in action for that one. I'm not going to do the whole thing. I just wanted to go through one. We have that a password requires 7 characters, okay? If a person who lives at 155 Nunn Road wants a password to be an arrangement of the characters 155 NUNN, how many different passwords are possible? Okay, so we're looking at a select number of characters. So in this case, we have let's see, we have these to work with, okay, with n is equal to 7 because that's the total number of characters. So this whole thing right here is equal to 7 characters. Okay, 1 would be equal to our 1 because that's one type of character we can choose from. Let's use a different color. Let's use this one. So K1 would be the ones, okay, number of ones, and it tells us right here. K2 would be the number of fives, okay. K3 would be equal to 3 because that's the number of n's that we have. So that's these parts right here, yeah. And K4 would be equal to 1, the number of u's. So you have a number for each number of distinct objects that we have. We have the 1, we have the 5s, we have the n's, and we have the u's, okay? And then we just plug them in. So the total number of items that we have is 7. So that goes on the top. So n is equal to 7. So we have 7 factorial, okay? And then everything else we just plug in. So we have the 1, there's the 1. We have 2, there's our 2. 3, there's a 3, and then 1, there's our 1. And then from here, you would just simplify. So notice that we went ahead and just went up to 3 factorial because we see that we have a 3 factorial down here, okay? So that one can kind of get rid of itself. And then here, 1 factorial times 2 factorial times 1 factorial, kind of a no-brainer because 1 factorial is just 1. 2 factorial is 2 times 1, so it's pretty much just 2. And then 1 factorial is also 1, which gives us that 2 that you see right here. Okay? Yeah, so pretty much from here, we just multiply these 4, divide by 2, and there's our answer. So this is just another example of what you might see if you have distinguishable characters and you have to arrange them in a certain order, okay, and a number of those characters. Let's go ahead and move on. So now we're going to talk about something called a combination. And I have an example here that I kind of just found, and I thought it was a pretty good example. And I want to know what is the difference between a permutation and a combination. So the one we just saw before was somebody doing a combination given certain characters, so a few numbers and a few letters, and they want to make combinations out of that. So here we have my fruit salad is a combination of apples, grapes, and bananas. We don't care what order the fruits are in. They could also be bananas, grapes, apples, or grapes, apples, and bananas. It doesn't matter. It's the same fruit salad. Okay, and you see that word combination here. And then we see the combination to the safe, so there's that word again, is 472. So in this one, we do care about the order because 724 won't work, 247 won't work. It has to be exactly 472. So since both of these have the word combination, does that mean that they're both combinations? Well, yes and no. So, if you read it, it does say the combination to the safe is this. But in reality, a combination is just a mix of items or elements. Okay, so this one up here would be your combination, where order does not matter. Okay, now, in the second one, the order does matter. So this one would be your permutation. And that's the biggest difference between a permutation and a combination. So really, instead of calling it a combination lock, they should call it a permutation lock. Just saying. Okay, so again, permutation, order does matter. So order matters. Combination, order does not matter. Okay, that's the main thing with these two items. Okay. So let's go ahead and do some combination examples now because we already did some with permutations. We have the number of combinations of n objects chosen k at a time is, and then we have our formula. So in this one, the order doesn't matter. It's just here are your objects, put them in some kind of combination, and how many different combinations can we get? Okay. So here's an example to kind of show this. An emergency room at a hospital has 11 nurses on staff. Each night, a team of 5 nurses is on duty. In how many different ways can the team of 5 nurses be chosen? So we don't really care what order the nurses are chosen. We want 5 nurses to be on staff at all times. So what we're going to do is we're going to go ahead and use this example with this formula. So let's see, we have 11 nurses total. So that would be our combination would start with 11 total, okay? And then we have to choose 5 of them at a time. Let's do yellow with that. So 5 nurses on duty. So that would be choose 5. 11, choose 5, okay? So this is going to be equal to, I mean, I guess you can do this one. Let's go ahead and do that. A permutation of 11, choose 5. But since order doesn't matter, we're going to divide it by this k factorial, okay, which is our total here. Oh, I didn't mean to put k. I'm sorry. I meant to put the 5. Here we go. 5 factorial, okay? So let's go ahead and work that out. It's going to be n factorial, so 11 factorial divided by k factorial, so 5 factorial times n minus k, so 11 minus 5, and then factorial. So it's just a few operations we have to work out. I'm going to go ahead and scroll down a little bit. I know that this part right here, 11 minus 5 is going to give me 6 factorial, okay? So I'm going to rewrite that as 6 factorial. And now I have all of this up here. So let's go ahead and write this nicer. So I'm going to have equal to 11 factorial on top. Actually, let's go ahead and just break it down now. So we know that we're going to go down to 6 for sure. So 11 times 10 times 9 times 8 times 7 times 6 factorial, okay? And then I have that 6 factorial on the bottom, and I have the 5 factorial. I'll deal with the 5 factorial in a bit, okay? So for sure, I can get rid of this part right here, okay? Which leaves me with 11 times 10 times 9 times 8 times 7 all over 5 factorial is 5 times 4 times 3 times 2 times 1. Okay, and then we just work this out. So let's do that really quickly. Hopefully you do have a calculator. If you don't, your phone will work just fine. Okay, so I'm doing the top right now, 11 times 10 times 9 times 8 times 7, and that's giving me 55,440. Okay, and on the bottom, I think I can do that one in my head. See, 5 times 4 is 20, 20 times 3 is 60, times 2 is 120, times 1 is still 120. Okay, so if I divide 55,440 by 120, I get 462. So this is equal to 462 different combinations that we can do with these nurses, with 5 nurses at a time from 11 total. Okay, I think we have one more. Yes, there's the last one. All right, so this example uses a little bit more multiplication. It says a committee of 5 is chosen from 5 mathematicians and 6 economists. How many different committees are possible if the committee must include 2 mathematicians and 3 economists? So now we have like a double choosing going on, if that makes any sense. We have to choose, I'm going to kind of color code this, of course. From the first one, we have to choose, let's see, 5 total. Okay, so we have 5 total. So I'm going to kind of go to the next sentence. How many different committees are possible? The committee must include 2 mathematicians. So we have 5 mathematicians. So from 5 mathematicians, we have to choose 2. And then we have to choose 3 economists from the 6 right here. So we have to choose from the 6, we have to choose 3. Okay, and this is essentially what we're going to be multiplying. We're going to be multiplying this piece, okay, times this piece right here. So this times this. We have to do like a double calculation here. So I'm going to go right into it. I'm going to go ahead and go right into the formula. I went ahead and included it here just for reference, okay? So it's n factorial divided by k factorial times n minus k. So let's go ahead and just set this up first. We have for this one, the 5 choose 2 would be 5 factorial over 2 factorial times 5 minus 2 factorial, okay, times, well, this one now. So now we have 6 factorial, the total number of economists, over 3 factorial, because that's our k, and then 6 minus 3 factorial. Okay, and then we just work them out individually and then go from there. So for the first one, I know I'm going to have 5 factorial over 2 factorial times 3 factorial. Actually, I don't have to put parentheses there anymore. So times 3 factorial, because 5 minus 2 is 3, okay, times 6 factorial over 3 factorial, and then 6 minus 3 is also 3, so 3 factorial. Okay, let's go ahead and simplify this now. So for the first one here, I'm going to go down to 3. So 5 times 4 times 3 factorial over 2. Remember that this one right here is just 2 times 1, which is just 2. Okay, so I'm just going to put the 2 times 3 factorial. And that helps me get rid of this, but I'll do that in a bit. Times, okay, 6 goes down to the 3. So 6 times 5 times 4 times 3 factorial over 3 factorial and another 3 factorial. Okay, so this one I'm writing both this one and this one, or these two. I'm going to go ahead and cross things out now. I can get rid of the 3 factorials here and the 3 factorials here. Oh, I'm almost out of space here. All right, so then I'm going to end up with 5 times 4 here on the top over 2 times 6 times 5 times 4 over 3. This right here would be 3 times 2 times 1. So that's going to give me 6. Okay. And then I can cross out a bit more. I can cross out the 6's here. And I'm left with 5 times 4, which would be 20 over 2. Okay. Times 5 times 4. Again, that's 20. Okay. 20 divided by 2 is 10. 10 times 20 is 200. So all that for this. Okay, so that means that for this committee, we have 200 different possible committees that we can make with these amount of people. Okay, and just like that's the end of our space here, that's the end of the video. So if you have any questions, as always, let me know.